In this lab, we will use EMLIB libraries. So in previous lab, we wrote values and bits or switches directly into memory registers to turn on the clock for GPIO or to turn on or off GPIO pins. But as we can see, this code is absolutely unreadable. It's hard to maintain such a code. And if we want to do some modifications, it would be very, very hard. And also, if you work for a company and then you change your job and go to work elsewhere and somebody else comes and reads your code, they wouldn't understand anything in this code. So the companies that build these microcontrollers, they also usually provide some pre-written code, also called libraries, with which you can control the chip much easier without writing some bits into strange numbers. You can use some beautifully named functions to do the same thing, but in much more manageable way. So let's use the EMLIB library, which is written by Silicon Labs programmers. And let's rewrite this lab work using EMLIB libraries. So first of all, let's look at the resources which we can use, which explain how the EMLIB library works. So first of all, we can go on the internet and we can search for EMLIB libraries, or you can go to this website, siliconlabs.github.io/gecko SDK doc/index.html, or you can just write EMLIB in the search. And I guess this first thing actually is the right one. This is EFM32 Giant Gecko Software Documentation EMLIB. So if I click here, or if I go to this web page and click Giant Gecko right here, it's the same thing, and EMLIB peripheral library. So the idea is that the microcontroller has many peripherals, which each has maybe 20, 30 registers with which the peripheral can be controlled. And the Silicon Labs have written drivers for them already. So let's see. First of all, as I mentioned, and it's a very common mistake for people who begin writing code for ARM processors, the most important library initially is the clock management unit library. So I click on it. And this library explains the clock management unit functions and how to use them. What are the possible values that you can use with the functions? So as I mentioned before, initially all peripherals are switched off and only the core is working, only the code is being executed. So for example, if we want to use general purpose input-output peripheral, we need to switch on the clock for this peripheral. So I'm just, giving you this information that clock can be turned on and off with Cmu library. So first we need to add this library to our project. How do we do that? First, we open this project tree, and under EMLIB folder, click on this msystem.c one time, right click on it and select browse files here. And this takes you to a folder which has all of these EMLIB libraries, the source code location. So we need to find em_cmu library, and we need to drag and drop this C file into EMLIB folder. And we should select link to files, because then the files remain in installation library and are automatically updated when Silicon Labs releases new updates. But we need to select create link location relative to Studio SDK location. So even if you install Silicon Labs in a different folder, the links will be correct and they will still work. So link to files, create link locations relative to Studio SDK location and click OK. And now, as you can see, next to this emsystem.c, which was initially included, there's a second file, emcmu. And I can double click on this file. The libraries are all open. You can go into them and read the code. If you found a mistake, you could fix it, you know. So these libraries are not, you know, hidden or some way unknown or unmanageable. So the first thing, we dragged and dropped em_cmu.c library into our folder. And the next thing that we need to do in our main.c file, we need to write hashtag include, and in the double quotes, emcmu.h. So we dragged and dropped the C file, which contains the code, but we need to add the H file, which is header file. I can control click on it, and this file has all the API functions. So there's a lot of code which is grayed out, which is for different series of Silicon Labs chips. So for example, here's some code which is in gray background because it's for Silicon Labs series 2. We have series 0. So if I scroll down, at some point there will be code which is not grayed out, which is for our series of processors. Here it is. So if we have defined Silicon Labs, oh no, this is basically for all of the series of chips. And here are some values that we can use to set to our processor. For example, in clock management unit, we can change the speed of our processor. Default value is 14 megahertz, but as we can see here, we can also select 28 megahertz or 21 megahertz, and we can actually make our processor run faster. And this processor can run up to 48 megahertz, but then you need an external crystal with a 48 megahertz frequency, and so on. So these libraries are written as universal as possible. So if you initially work with EFM32 Giant Gecko, but then you want to use a different chip from Silicon Labs, they have written the libraries in such a way that you can use absolutely the same code and it will still work. First of all, because it's ARM processor, and secondly, the libraries are written universal so that the code automatically changes depending on the series of your processor. So let's try to use the Silicon Labs EMLIB API to turn on the clock for GPIO. So to turn on the clock of GPIO, some bit needs to be set in this clock management unit register. But Silicon Labs guys have written a beautiful code, a beautiful function, which is called Cmu underscore clock enable. And you give a parameter which clock and whether it should be turned on or off, because to save energy, you sometimes want to switch some clock off, and to use the peripheral, you need to turn it on. So Cmu clock enable is the name of the function. How did I know the name of the function? First of all the functions are written in this Giant Gecko Cmu library documentation, and there are many of these functions, but you know, you can just skim through them. You can see that there's a lot of functions that you don't need. For example, calibration, you don't need that. Clock div get, blah blah blah. But here is Cmu clock enable. So there's a function which enables or disables a clock, and it accepts two parameters: which clock and Boolean, whether it should be enabled or disabled. So true will be enabled and false will be disabled. And the clock names you can find here, Cmu clock Typedef. if you click on it, you get a list of allowed values. So CMU clock underscore and then the clock name. So all of them start with CMU clock underscore, and then you have some options here. And we need CMU clock underscore GPIO to be switched on. So I can just copy this name, paste it inside the brackets, put comma and write true. And this line enables general purpose input output clock. Okay, so I will delete it and show you a trick. So in this Simplicity Studio, you can write the beginning of the function. So I'll write CMU underscore, and when you click Control and spacebar, this menu pops up with all the functions which start with CMU underscore. And here you can also find the list of the supported functions. So let's say I don't know the function name, but I think it should be something about enabling a clock. So here I find a function called CMU Clock Enable, and this is actually the right function. So I double click on it and it's automatically completed. And the cursor is inside the brackets of this function. And if I click Control Space, it also shows me what arguments I can input in this function. So the first argument is Cmu Clock Typedef Clock. So it's some predefined clock name. And the second is enable. It's written here integer. In the documentation, it's Boolean, but basically it's 1 or true to enable and 0 or false to disable. So I don't know the clock names. I don't know what the CMU clock typedef is, but if I write CMU and click Control Space, here it actually shows me some options, and here I can actually find CMU clock GPIO. So intuitively, I can just guess the correct code. So I double click on this, but see, there's no underscore between CMU and clock. So you write CMU, control space, and you get this help text, put comma, and then control clicked and control space, and you can see the second argument in bold int enable. So I can put 1 or true. I'll write true because historically it's the way how this library was written. So now this function, this line, does absolutely the same as this line, except it has a beautiful name. If we control click on CMU clock enable, we can go to the implementation of this function. It's all open code. You can read through the code and try to understand what it does. It checks the clock name, and depending on the clock name, it finds the correct register to write the value, and then it writes either 1 or 0 to the corresponding bit. So this second part is just the bit to be written in this register. So, you know, there are many clocks, so it goes through the clock name until it finds the correct one. So if we gave the name of the clock GPIO, somewhere in this list there is GPIO clock. Let's see, correct position. You know, it will find the correct clock in this case, in this list, and it will enable it. And then just exit. Everything is just written in beautiful C code. And if you don't know the argument names, you can control click on the function. You go to the function, you have this argument CMU clock typedef, you don't know what it is, you can control click on this type name, and it will, after, I don't know why it doesn't work, sometimes doesn't, I don't know, save all. But basically it takes you to the list of possible clock names, and you can also copy the clock name from this list. Okay, so After writing this line, it does absolutely the same thing as this line. So these weird things we can just delete. And now I can build the code. It built successfully. However, the thing is that this code size increased from 800 bytes, something like 900 bytes, to 1,800 bytes, because these libraries, to be universal, they are a little bit bigger than if you write directly values into registers. So this one line is basically one or two instructions. So it takes only one or two words in the flash memory. However, this function, it goes through multiple names of the clock sources until it finds the correct one, and then sets or clears it. So this library, this function is heavier, it's bigger than writing bits directly into registers. So that's a little bit of a disadvantage of this using these libraries, but it's a good trade-off because this code is much more easily manageable than these register numbers. So this first thing is done, and the second thing is the GPIO. So general purpose input output library also exists. First of all, we can check it out by right clicking on this either cmu.c or emsystem.c, right click and browse files here. And in this folder with energy micro libraries, this EM stands for energy micro. Here's also em underscore GPIO. And intuitively, you know that this library probably controls general purpose input output pins. It's true, so we drag and drop it into EMLIB folder. We select link to files, and in dropdown we select Studio SDK location, click OK, and we have gpio.c library attached. And in our file, we need to write hashtag include, and in double quotes, emgpio.h. So we include the C file, we drag and drop the C file, but include the H file. That's how these libraries are constructed. So if we have GPIO library attached to our project, we can either go to gpio.h and look at the names of functions, a lot of grayed out code and stuff like that. But here we can see the port names. We can see drive mode strength. We can see the modes, disabled, input with pull up or pull down, push pull mode, and so on. And also the function names, but it's a little bit hard to orientate yourself in this H file. So we can also go to the documentation, and on this left side of the screen, we can find GPIO library. I click on it, and here I have the library condensed in a smaller space. So let's see the functions of GPIO library. For example, GPIO drive mode set. So we select which port and what mode we want. This is drive strength, or GPIO pin mode set, where we can tell which port and which pin should be in what mode and whether it should be high or low, or pulled up or pulled down. So we will use this GPIO pin mode set to set the mode of the pin. So initially we wrote some value of pin mode into some register, but now we will use a beautiful GPIO API function. So again, I can write GPIO underscore and press Ctrl space. And I already have a menu with all the function names. And here I find pin mode set, GPIO pin mode set function, which sets the mode of the pin, input or output, pulled up or pulled down, high or low. Now we will go back to the documentation of the development kit. So let's see. This board SDK documentation. User's guide, I guess. Yeah, here's the user's guide. Oh no, this is probably the right file, just for an older version. But all of these development kits, they try to build them, that they are forward and backward compatible. So on all development kits, the LEDs are on the same processor pins. So I'll use this document as well. You can use the one that we used in previous document. But here it says that LEDs are on port E pin 2 and pin 3. So what we need to do in our code, I go back to simplicity IDE, and here GPIO pin mode set. First argument is port name in the special way that they have defined it in this API. If you don't know the port name, you can control click on this function and go to port typedef. And here you can see the names GPIO, port A, port B, C, D, or E, or F. So how did I get there? I control clicked on GPIO pin mode set. And here the first argument is GPIO port typedef. I don't know what it is. I control clicked on it. And it takes me to the list of valid port names. And I check out in this document that the LEDs are on port E. So I just find port GPIO port E. I copy the name and I paste it here as the first argument. Then I put comma. The second argument is the pin number, and it's just the number of the pin. So pin 2, so it's just number 2. I just write number 2. Then the third argument, control space, it says the mode, but in the special GPIO mode typedef format. So I control click on this function again. I find this mode typedef thing. I don't know what it is. I control clicked on it, and it takes me to the list of valid mode names. And what I need is the mode which is called push pull. So here it is, GPIO mode, push pull. It means that it's a fancy name for just output, which you can set high or low, and it will either give out 5 volts or give out 0 volts. So I copy this push pull name and I paste it here. And the fourth argument is whether I want it to be initialized high or low. So in this case, the LEDs are in active high configuration, which basically means if I set the pin high, the LED will shine, and if I set it low, the LED will be off. It will not shine. So initially, I will initialize it to 0, which is LED off. I'll write a comment for this line. Initially, let's say the LED is switched off. It doesn't shine, but it's configured as output. And if I want to, I can set it high at any time. So I'll write a comment, set port E pin 2 as output low initially. And I can just copy this line, and to set the second LED, LED 1, as output, I just change port E pin number to 3. So here I write 3, and these two lines initialize port E pin 2 and port E pin 3 as push-pull low. And that's it. I didn't have to go into datasheet and scroll through all of these register names and bit fields to find which bit should be set or cleared to set certain mode. I just use this API. However, it doesn't mean that you need to entirely switch off your brains and not think for yourselves. You still should understand that these functions are not some black magic. They just simply help you set or clear bits in the registers. And you need to know this because if one day something doesn't work, then you know that you can use debugger and look into the registers for the values, compare them to the datasheet values, and maybe you can find some mistake there. So these two lines beautifully set the port E pins 2 and 3 as outputs low, so I can delete these two lines as well. And to set a pin high or low, there are two functions which are called Gpio pin out clear, pin out set, or pin out toggle. With one, the names are self-explanatory. With pin out clear, you set it low. With pin out set, you set it high. And with pin out toggle, you toggle it to the opposite value. So if it was high, it turns low. And if it was low, it will turn high. So just three simple functions. So I will delete, well, let's say in this line, I want to set the pin high of LED 0. So I will use this API called Gpio pin out set, Gpio port E, pin 2, and that's it, no more arguments. This is basically set port A2 high. Okay. And I can control click on this function and check out how it works. And basically it writes 1 shifted by pin number into a certain register, which basically switches the bit on, so it's high. And pin out clear will do the opposite, it will clear the register pin. And in our infinite loop, so instead of switching the registers on or off with this line, I delete it and I just write Gpio pin out. What was the code? So first of all, we set LED 0 on and LED 1 off. So GPI pin out set Gpio port E pin 2 and Gpio pin out clear Gpio port E pin number 3. So this thing turns on LED 0 and this turns off LED 1. Then we delay 1 second and I can just copy this, these two lines and paste here and just swap pin out set pin 3 and pin out clear pin 2. And this code, I'll build it to see that there's no mistake. This code turns, one LED on and the second off, waits 1 second, and then it turns the other one on and the first one off and waits 1 second. So the LEDs should just switch between one being on and the second being on. And as previously mentioned, now our code size is 2,500 bytes. So by writing directly to registers, the code size was only 870 or 900 bytes. And now using these EMLIB libraries, it is 2,500 bytes. So the libraries make the code bigger. It's true, but it's more manageable. So basically, if you're building a simple project, money is not an issue, and you can take a processor with bigger flash memory, then you just write the code in this way. And if it's super advanced project where you need to squeeze a lot of code into a smaller processor for whatever reason, then sometimes people write some libraries not using these EMLIB libraries, but by writing some values directly into memory. So I have to teach you that, I have to mention you that, so that you are able to do it. But generally, we will not do it. We will use these EMLIB APIs. But you have to know that they take more space in the memory, and if you need to squeeze something in smaller memory, then you might need to write some values directly to registers. Okay, so let's build this code. I will flash it into the processor. So this hex file, I right click, flash to device, program, and now I'll look at my development kit. And it looks like it works. The light switches between one LED and the second LED. So it looks like it works. Okay, so this code is beautiful, but it has one problem. If a person, just sits at this code, a third person comes to this code and they look at it, they don't know what it means that GPIO pin outset GPIO port E2 does. So I could write a comment here, and so that the person knows what this pin does, I can write turn LED 0 on. And for the second line, I can write turn LED 1 off, right? And for the second part, I can write comment turn LED 1 on. And for the final line, turn LED 0 off, right? The name of the function delay 1 second basically tells us what the function does. It basically says delay 1 second. So for this line, I don't write a comment. You don't have to comment lines which are self-explanatory, but the lines that are not self-explanatory, you should always write a comment, even for yourself. If you write a code and then you work for a couple of weeks on a different code, and then you return to the first code, you should be able to understand what it does, right? So here, since this line GPIO pin outset is not self-explanatory, it doesn't tell what physically this action does, I write a comment that it turns LED on, and a third person can come up to this code and understand what it does. However, this is not the best way to write the code, because it's still hard to understand what the code really does. So there is a law in programming which, first of all, forbids use of magic numbers. So if the code has magic numbers 2 and 3, it's a bad code, because how can I know what this 2 means? Secondly, this GPIO port E is also not a good way to write a code. The correct way to turn LEDs on and off in a good, well-written code is the following. In the beginning of the code, we define the names of ports and pins of LEDs, and further in the code, we use the name LED port and LED pin or something like that. So the good way to write the code is the following. In the beginning of our code, we write hashtag define, and then we define, for example, LED 0 port, GPIO port E. Next, we write hashtag define, LED 0 pin, and LED 0 pin was pin 2. Then we write hashtag define, LED 1 underscore port, also GPIO port E, and hashtag define LED 1 pin 3. So LED 0 was on port E pin 2, LED1 is on port E pin 3. And in the code, instead of writing GPI port E, 2, and 3, we write this name LED0 port, LED0 pin, LED1 port, LED1 pin instead. So I'll show it to you. So I copy this name LED0 underscore port, and I paste it here and here and here. Okay, I'll delete this line. We don't need that. And where I mention LED0 pin, instead of writing 2, I write this name LED0 pin. So here, here, and here. Then for the places where I'm working with LED1, I use this LED1 port name. So here, here, and here, I write this, and then LED1 pin, I copy it, and I overwrite the 3s with this name, here and here. And now, basically what it does is this hashtag define, when the compiler compiles the code, it finds locations where it says LED0 port. In all of these locations, it in the background deletes this name and replaces with this GPIO port E all the occasions of LED0 pin. It replaces with number 2. So basically, and for the same is being done for LED1 port and LED1 pin. So basically, the code for compiler looks the same, but for programmer, this code looks much better because check it out. Now, when we read this code, we see that, for example, here it says GPIO pin outset, and instead of some GPIO port E and 2, which we don't know what it is, it says pin outset for LED0 port LED0 pin. So now we don't have to put these comments here because these lines become self-explanatory. This says pin out set for LED0, pin out clear for LED1, and the programmer, even if they have never worked with this code, they immediately understand what this code does. So this line sets LED0 on, and this code sets LED1 off, clears it. And the second line, LED1 port, LED1 is set and LED0 is cleared. So intuitively, the person understands that this line turns on an LED and this line turns off the other LED. So in good code, you define ports and pins with these hashtag defines and add them some beautiful name, which is self-explanatory. And then later in the code, you use these beautiful names instead of magic numbers. So magic numbers are forbidden, right? For example, Gpio Mode push-pull translates to number 4. As you can see, if I select this text and highlight it and hold the cursor on it, it says 4. If I control-clicked on it, this brings us to enumeration, which is 0, 1, 2, 3, 4. But we, instead of using magic number 4, which would compile to the same thing, a beautiful name is used. So this is very important. So if I build this code, the code size is absolutely the same. It's a little bit smaller because I deleted this, this one line that was here. But basically, the code is the same, but it's much more readable. So this is the correct way to program. You define pins and ports initially, and then later in the code, you use the beautiful names. And so you can compile this code and flash it into your development kit and see that it works the same way and there are no mistakes. If something works wrong, probably there's a typo in your code. And the problem with LEDs is that sometimes you can have them in a active low or active high configuration. You know, you can connect LED to ground or to power supply. and GPIO pin. So oftentimes, even this line is considered to be hard to read. So again, we can actually use this hashtag define, and we can define LED 0 on, which will be, you can basically just copy this line and hashtag define LED 0 off, and you can copy this line, and the same goes for hashtag define LED 1 on and hashtag define, oops, LED 1 underscore off. There is a convention that hashtag defines are written in caps lock, in capital letters, and separated by underscore. This tells you that this is defined thing, which will be copy pasted or replaced during compilation. It's the opposite of functions, because function, you actually go into the function and do all the things that are written in the function. So it's a function call. Hashtag define is just copy paste replacement. Let's see. LED1 on is GPIO pin out set in our case. And LED1 off is pin out clear. So we define it this way, and in our code, instead of this line, we write LED1 on. And again, I can write LED1, control space, and I have offered some predefined values. So I want to use LED1 initially off. Oh, sorry, I'll write it a little bit differently. So LED 0 on, LED 1 off. Oops. Like this. And for these lines, I'll write the same LED 0 off and LED 1 on. LED 0 on, LED 1 off, LED 0 off, LED 1 on. I can compile this code. As you can see, the size of code is identical, it's the same code. It's just that we defined more beautiful names to these GPIO pin out set and pin out clear, so that the person that comes to this code, they immediately understand what this code does. And if you need to change the configuration, if, for example, you make a board and LED pin, you suddenly use a different pin, you only change the pin number in one place in the code. For example, pin number 7, you have pin number 7 for LED, and all the code is automatically updated and changed in such way that LED pin is now pin number 7. Instead of changing the pin number in every place in the code where you used it, you only define it in the beginning of the code, and in the rest of the code, you use this predefined name. So this is the second huge advantage why everybody is using hashtag defines for general purpose input output and all the other peripheral access, so that you configure it in just one place in code. In the rest of the code, you use this predefined name, and if it changes, you just change it in one place in the code. Okay, so I build this code. Oh, sorry, I'll change it back to pin number 2. I build the code. I flash it into the development kit. And I can check out that it still works the same way as before. So LEDs just change which LED is shining, and that's it. Okay, so next thing is we should also learn one more trick, which is really good, is that usually if we have multiple peripherals, we try to break the code into separate files. Each file is like a small library for each peripheral. So right now we have LED control in this main file, but if we add UART, if we add timers, this page will become, I don't know, 1000 lines long, and it will be very hard to manage. And if we write something, we can accidentally break something. So the convention is that we want to put control of each peripheral in its separate file. So what we're going to do now is we're going to make a small LED control library, and we will move all the code that controls LEDs, for example, these lines, into a separate file so that we write it, we save it, and we never touch it again. And we just use the API. So what we do now is on the source file, right click and select new header file, and we will name this file leds.h, and we press finish. And then we click on the source file, new source file, leds.c. So the library consists of two files. One is the H file, and the second is the C file. The H file only contains the functions that the other code can call, like LEDs init, LED on, LED off. And the C file contains the implementation of these functions, like the actual code that is run when you call the function. And there is this convention that in the C file, you only include hashtag include, and in double quotes, the header file, leds.h. And in the H file, you include hashtag include all the libraries that are necessary for your C file. And to control LEDs, we use Gpio library. So obviously we include Gpio, right? So it's just the way that most programmers organize their code. So in H file, you write all the includes and all the API function names. And in C file, you include only the H file and write the implementation of the functions. Okay, so I'll just show you how it's usually done. The first function that we want to define in our leds.h library is the initialization of LEDs. So instead of having in main code some weird lines like these, we want to move them into the C file of LEDs library and have only one function, which is called LEDs underscore init. And this function type is void because it doesn't return anything. And its arguments are no arguments, which is void. This is how it's written. So void LEDs init void. We copy this, we paste it in the C file, and we delete the semicolon and put these curly braces here. And here in the C file, we will copy all these magic things that are in the H file. So first of all, I'm going to copy the LED port definitions to the C file, like this. Secondly, into LEDs init, I copy the initialization of LEDs. Then I will also define two functions for LEDs, and usually we don't want to have extremely many function names. So to turn on and off the LEDs, we will use this following function, void, and we will call it led underscore on. And as an argument, we will pass which LED we want to turn on and off, LED 1 or LED 2. So it will be, sorry, LED 0 or LED 1 because they are enumerated from 0. So LED 0 and LED 1, so I'll use the same numbers. So the argument will be integer int led number. So whether it's 0 or 1. And I will copy this function also into the C file. And so and we will also have a function to turn LED off. So void led off int led number. And I'll also copy this. And now we need to write implementation of LEDs on and off. And the argument will be led number. And to do it properly, we will write the code in the following way. We will initially write it in, a very simple way. So how to turn LED on? We can actually copy these defines also into our LED.c file here. And so basically what we will write here, LED on and LED off, in the simplest form, it will be like this. If LED number equals to 0, so if it's LED 0, then we will use this LED 0 on define, and else if LED number equals 1, we will call LED 1 on. And for LED off with the argument LED number, basically we will do the same. If LED number equals 0, then LED 0 off, else if LED number is 1, then we will call LED 1 off. Like this, very simple, code, and we're using the same definitions, and now we can save all. So I'll show this code. You can pause the video and, type it down into your Silicon Labs program. Then LEDs.h code looks like this. And the main code we will edit. First of all, in the main code, we are not using GPIO anymore. So I can delete this hashtag include because we will use the API. Now in the main code, if we want to control LEDs, we need to include LEDs library. So I write hashtag include leds.h. I include this library. It's necessary, otherwise this thing will not work. So I include leds.h. Then in the main code, I first need to call leds init so that they are set as outputs. And I call it leds init. And I can control click on this function and it takes me to this place here and into this file, and it's right here. And in our infinite loop, instead of writing LED 0 on, LED 1 off, and something like that, we will write it a little bit differently using LEDs API, LEDs or what was the name? Led on, led number 0, and led off. Oops. Led off, led number 1. And the next lines, led off, led 0, and led on, led number 1. Now I build this code, and let's see if it's going to build. So it looks like there are no problems. The code became a little bit bigger. Previously, it was 2,500 bytes. Now it's 2592. The code became a little bit bigger because function calls are a little bit bigger than hashtag defines. So when we use just hashtag define, it was not like another nested function call. It was just go directly to this function. But now we are using function calls, so it's a little bit bigger, but not much. But this code is even more readable and more universal. This main code doesn't contain some hashtag defines anymore. It just uses some functions which we have written, but they are hidden in separate files, which if we close these files, we cannot actually accidentally delete something from them and make the code hard to manage. So I built this code. I flash it into development kit, and let's see if it works. And I look at development kit, and the code still works as necessary. Okay, and finally, one more modification. This code LED on 0 and LED off 1, it's still hard to understand. I don't understand what this 0 and 1 does. Is it on 0, on 1? I don't know. So the correct way to improve our code and make it even better is with a new concept. Maybe it's new for you. Maybe if you're experienced programmers, you already know it. But instead of using LED number as magic number, we will use something called Typedef Enumeration, and we will give names to 0 and 1 in a more beautiful way. In the following way, we will create a new type, a variable. So it's written like this: type def enum, curly brackets on, open, and we write, for example, LED 0, comma, in new line LED 1. And before closing this, we will write led numbers t. And with this code, it creates a new virtual variable type, which is called led numbers. And the allowed values are named LED 0 and LED 1. And actually, enumeration simply gives numbers starting from 0 to all the members that are inside this enumeration. So actually, LED 0 means 0. It's similar to hashtag define. It's just that you don't have to write hashtag define, LED 0, 0, hashtag define, LED 1, 1. This thing automatically enumerates from 0 to n all the members of this enumeration. So LED 1 is number 1. It is equal to typing hashtag define led 0, 0. And for this, it is equal to typing hashtag define led1.1. You know, it's a nice way to enumerate things, enumerate definitions from 0 to n as integers. So it's very often used. And here, for example, if we go to EMGPIO, in the location where the GPIO port names are given, they're also enumerated here. Check it out, Typedef Enumeration, GPIO port Typedef, port A means 0, port B means 1, port C means 2, port D means 3, port E means 4, port F means 5. Actually, port names are just numbers. It's just that it's easier to use these human readable names rather than some magic numbers. So they're enumerated here, and they wrote equal to 0, but it's not really necessary. It could have been just, you know, port A and that's it, because they're automatically enumerated from 0 to n. It's just that possibly some CPU doesn't have port A, so it's, you know, not enumerated at all. And then the next port should be started by 1. But in our case, it's automatically 0 and 1. And the second advantage of using these enumerations is if you define a function and the argument instead of integer is LED numbers underscore t in both places, then these integrated development environments, when you type the function names, they offer you oftentimes automatically to select one of these enumeration types because the arguments are of this type, so they can automatically offer you the value from this list. So good integrated development environments will take advantage of this typedef and automatically offer you only one of these two values. So this is how we will define our function. Then we need to also update our C code. And in the C code, we also say void LED on, instead of integer, use LED numbers t. And here the same. And also, by the way, enumeration type is actually integer. It's just with predefined values. So enumeration is int, it's the same thing. So our code, when we compile it, it will not even change. But now we have LED 0 and LED 1 options. We save all of these files. So this is LED H. You can double check that you have written it correctly. This is LEDs.c. You can check out that you changed this part. And in main code, instead of 0 and 1 magic numbers, we will use LED 0 for zeros and LED 1 for instead of 1. And now the code is even more readable. And also some integrated development environments check that you're using correct names of the numbers. And if you're using something different, some compilers will give you a warning that you are putting in a wrong argument, which also helps to find mistakes. But now the code became even more readable, which here reads now LED on, LED 0, LED off, LED 1. You immediately understand without any comments what this code does. This is the reason why you might think, oh, this is so excruciating. I had to write so much code to simply turn on and off LEDs, but it's well worth it because when it's all done, you have these self-explanatory functions which are easy to maintain and update. So now I will build the code. The code size is, you know, practically the same as was before. And now I can flash it into, I can flash it into the development kit and check out that it works. And I see that it works. So that's great. Okay, so this is done. Your task now is to write down this code for main.c. You also need to create leds.h and leds.c. Write down this code. Yeah, one more modification, it should be here. So instead of comparison to numbers 0 and 1, you know, magic numbers, we should actually compare to the typedef names. But as you saw, it works because LED 0 translates to 0 and LED 1 translates to 1. So the code was working before, but to make it as beautiful as possible, we should be using these names. I build it. The size is the same. The code is actually the same. It works, but now it's, you know, the best that we can get. So now you can just write down this code in your development environment, compile it, flash it, try to understand how it works. This is .c file. This is .h file. This is the main code. And, you know, so that you are doing something on your own, now you need to change the code so that initially both LEDs turn on and then both LEDs turn off. Update the code so that both are on, then both are off in this forever loop, and upload it to Ordus so that I can check it. So that's all for now.